Right, this is a worked example for a differential equations problem to do with a cone of water. Now, this actually is quite a tricky problem. This is one of the hardest ones, A-level um, problems I've seen in differential equations, but as such, it does have a couple of really good learning points in it. So it's definitely worth having a look at. So let's have a look at the question. Water is poured into an empty cone at the rate of 8 cubic centimeters per second. After t seconds, the depth of the water in the cone is h centimeters. So you see, it starts off empty, and then we fill it up, and it's the that's the rate of change of the volume. When the depth of the water in the cone is h centimeters, the volume is given by this equation. V equals pi h cubed over 12. We'd probably recognize that as one of the standard volume formulas. Okay, so then the question is, show that when t equals 3, dv dh equals this weird thing here, 6 times the cube root of 6 pi. Right. Okay, so how are we going to do this? Right, we're looking at this question here, dv dh. Show that when t equals 3, dv dh equals this number here. Well, the problem with this, of course, is that well, we can look at this equation here. Can we not get it from here? V equals this. Well, we can differentiate this to get dv dh, but of course that is a function of h, not a function of t, and we can only evaluate this if this is going to if we've got dv dh as a function of t. So what can we do about it? I mean, it would be good if we had some conversion between h and t. You know, h is a function of t, and t is a function of h. But we don't seem to have that. Well, actually, we do, and it's not straightforward, I have to say. Let's have a look at this. We're given this information, empty cone at the rate of 8 cubic centimeters per second. So we can write that dv dt equals 8. That's what we've got. Now, the trick here, which is not obvious, I have to say, is if we integrate this, we're going to get this v equals 8t plus c. We just integrated both sides with respect to t. V equals 8t plus c. And if we apply the boundary condition that is implicit in this statement, poured into an empty cone. So in other words, when t equals 0, v equals 0, and h equals 0, but for our purposes, v equals 0. And if we apply those boundary conditions, then that's simply going to give us v equals 8t. All right, so that's useful, but that's not the end of the story here. Now we've got v equals pi h cubed over 12. Aha, c. Now we've got v in terms of t there, we've got v in terms of h there. We can bash these two together, give ourselves this equation, 8t equals pi h cubed over 12. And this is our relationship between t and h. Now, really what we want to do is we want it the other way around. We want it explicit in h, because once we've differentiated dv dh, that's going to be in terms of h. So then we need to be able to substitute for h in it. So anyway, if we just turn this equation round, we got h equals the cube root of 96t over pi. All right. Now we've got dv dh. Well, by differentiating this, we've got dv dh equals pi h squared over 4. But from here we've got this h, this substitution to make for h. So we're going to stick that into there, and we're going to get this horrible looking thing here, dv dh equals pi over 4 into all this lot here, 96t over pi to the power of 2/3. All right, you might just need to pause the video and just satisfy yourself of that, but that's basically what we've got. Now, we're asked to evaluate dv dh when t equals 3. Well, we can do that now. plug t equals 3 in there, and we get well, I mean, there's a bit of kind of tricky little work in here. Effectively, it comes out to 6 times the cube root of 6 pi, which is what we're asked to show. Now, again, pause the video and just have a look at this bit of working here. It's a bit messy, but you know, it'll you can work that through for yourself rather than me talking it through. Right, so that is that. And I think that probably there's 2 keys, aren't there, to actually solving this. I think first of all we've got to recognise that we can easily get dVdh, but in terms of h, and therefore we need to be able to have h as a function of t in order to be able to get dVdh in terms of t. How do we do that? Well, yeah, I mean, it's really kind of not terribly obvious and a bit obscure, but what we're going to do is we're going to get ourselves through this. We're going to get an equation for v in terms of t, and that effectively is going to give us a relationship between t and h. Okay, not easy to spot, but you know, you might get something similar to this in your own A-level problems examination. So that's that. Anyway, that's part A. We've got a part B here. So let's just have a look at part B. Hence, find the rate at which the depth is increasing, that's h, when t equals 3. Give your answer to 3 significant figures. Okay. So now the rate at which the depth increases is dh dt, and in the lessons videos, I think, you know, we've exposed this fact that we can basically expand out this dh dt using the chain rule, but it's kind of the chain rule backwards. So we're expanding it out into dh dv times dv dt. Now this is dh dv, which is 1 over dv dh, but that's okay. We can cope with that. Again, is the chain rule effectively. So since we've got dh dv, therefore is 1 over this expression that we got from higher up. That's the sort of that's before we substitute t equals 3 and simplify. But anyway, I've just left it like that. And dv dt equals 8. That's from the problem statement. So if we bash those 2 derivatives together, we're going to get this expression. And if we sub t equals 3 in there, well, we know what's going to happen to this because we've just done that in the part A. So it's going to come out to this crazy little thing here. So that's what we've got, 8 over 6 times cube root of 6 pi. And we can just plug that into our calculator and it gives us this answer. It's asking it for 3 significant figures. So if we work that through, that's 0.501. And that's the rate at which the depth is increasing. So that's in centimeters per second. So yeah, tricky problem that. If you get one of those in your A-level examination, then you know, that's going to be as hard a problem, I think, as you're going to get at A-level, if I'm perfectly honest. But it can be done. And so if we just think of the key learning points, you know, but first of all, I think, you know, just spot that, going back to this, that we can only evaluate dVdh at t if it is a function of t. So that, you know, that's if you kind of have that sort of operation in mind, then it should get you started on any such similar problem. So really, that's quite a tough one, but hopefully you found that interesting and useful. So thanks for listening.